What's up, buddies? It's been a while, I know, but today I'm bringing you a course that I think you're going to really enjoy. It's about video agents. I think this is one of the first open source courses that I made about this topic, and we are going to cover three basic components. Okay, we are going to cover MCP in detail, creating a production-ready MCP server, how to expose the prompts, the resources, and also the tools, of course, and everything related to video processing tasks. Apart from that, we are also going to create, as always, an agentic API. This is something that I've done in previous videos, but in this video, in this course, I didn't want to use any kind of framework, so no LangGraph, no LangChain, no Llama index, just your own Python skills, basically. And finally, we are also going to cover, this is something that we missed in the previous video in Philo Agents. In this video, I just wanted to cover all the front-end stuff because we have created a pretty complex front-end application using React, and I thought this time it could be interesting to cover all of that in detail because I think it's a skill that many data scientists, even machine learning engineers lack. So yeah, that's the reason why we decided to go with front-end 100% this time. And of course, as you can see in the thumbnail, I'm not alone for this course. There's a co-author. His name is Alex Razvant. He is another content creator and also a friend. And we decided to go with this together. But let's let Alex introduce himself. So whenever you want, man.
Hey everybody, my name is Alex. I am the one with the beard from the thumbnail of this video. And recently I've joined forces with Miguel to build this new course and make it open source, where we'll be going through each component step by step, such that you'll not only get the chance to learn, but also work with AI agents, multimodal AI, MCP servers to expose tools and other capabilities to your agent, various LLM models, VLMs, and embedding models. But most importantly, a critical aspect for it will be building the entire system. So you will have the chance to build a backend API to host your agent, and also a front-end application that is user-facing, and then have everything connected and deployed in a reproducible manner. Now, all these details might sound complicated at first. You don't have to be an AI expert to take this course, mainly because we aimed for it to be general audience friendly, while still keeping a fair amount of technical depth to it. So throughout this video, you're going to see me here and there, where I'll be explaining a few concepts in more depth, such as the multimodal pipelines, how VLMs work, what is the video format, types of images, and so on and so forth. So for now, I'll be leaving you with Miguel, and I'll see you soon.
All right, thanks for that great intro, Alex. And now it is time for us to show you what Kubrick, this video agent, is able to do, and we are going to see it with a very short demo. So, demo time. All right, so demo time. I've just equipped myself with the headphones, so I'm in full builder mode right now. So what you can see on the screen right now is basically Kubrick, or to be more specific, is the front-end UI that we are going to use to interact with Kubrick and also the MCP server. On the right, you can see this video library. This is the place where you will be uploading different videos that you want Kubrick to process. Here, I've uploaded a very famous scene from Infinity Wars, from Avengers Infinity Wars, in which Thanos is snapping his fingers to erase 50% of the universe. Okay, maybe I'm pretty sure that you know this scene. And in here on the left is the place where you will have the chance to interact with the video processing agent. So I'm going to use this clip, this Thanos clip, as a test sample, and we are going to ask Kubrick different questions to showcase the different functionalities. Okay, so let's start with a first question. It's going to be like this. So show me the clip where Thanos says, what was the sentence? You should have gone for the head, I think it is. This is the scene that, this is the sentence that he says to Thor when Thor tries to stop him from snapping the fingers. Okay, so what this is going to trigger internally is a call to a tool which resides in the MCP server. The agent is going to use this tool to cut a clip from the overall video, and is going to send us back this clip, okay? You will see it in a few seconds if this works. So you'll have to wait for a couple of seconds, and you should see here, yeah, this is the clip. So if we run the clip now,
You should have gone for the head.
okay, yeah, so I remember correctly the phrase. So in this case, it's not that difficult because we have explicitly said the sentence, more or less, that Thanos was saying. But we can also ask about specific actions or specific descriptions about a scene, okay? Things that are not said by any kind of character, but descriptions about different scenes. For example, show me the clip where there are people disintegrating. For example, you know, when Thanos snaps his fingers, people start disintegrating. So let's see if Kubrick is able to detect this scene and is able to generate a cool clip about it. So let's wait again for a couple of seconds, and hopefully, let's see if Kubrick is able to generate something cool. All right, so looks pretty good if you ask me. So, okay, so here we can see Scarlet Witch being disintegrated. Oh man, this is so sad. But it's also a very good ending, if you ask me. Probably it's my favorite Marvel movie. And finally, I'm just also going to show you something really cool, because you can also, you can also use some images. For example, here I have an image about Rocket Raccoon, and you can ask, show me the clip where Rocket Raccoon, I think it's like this, it's Rocket Raccoon, but maybe I'm wrong, where Rocket Raccoon appears in the scene. And it's going to use this image as the information to search for relevant frames where Rocket Raccoon appears. And then it's going to cut the clip where this frame, where the most similar frame appears. You will see that all that we are doing is basically video rack. This is something that we are going to explain later in the video, but even if it seems like kind of magic, you will see that it's extremely simple to understand. Alright, so it looks really cool. Rocket Raccoon. Oh, this is also a very sad scene. Groot. Alright, and here it's repeating Scarlet Witch disintegration. But yeah, this is basically some of the functionalities that you will find with Kubrick. And now that you understand how it works, not how it works, now that you understand the functionalities that this agent is able to provide, we are going to get into the interesting part. We are going to get into how all of this is implemented from scratch, how all of this is implemented. We are talking about the MCP server, we are talking about the agent API, and we are also talking about the UI that you are interacting with. In this open source course, we are going to cover the three parts in detail. So, if you're ready, let's get into it. What's up, friends? So here we are, ready to get started with this coding journey. So as always with my videos, everything starts with a repo. In this case, the repo is called Multimodal Agents course, and it's located in Alex Razvant's organization, GitHub org, Multimodal AI. Okay, so you can go there. I will leave the link in the video description. And as soon as you get here, you will very quickly notice this beautiful diagram by Alex. I think this is pure art, to be honest. It displays the agent API, which is one of the three components that we are going to build today. Okay, the Kubrick API, the Kubrick application is built upon three basic components: the MCP server that you can see in here, the agent API, and also the user interface. But this is something that I'm going to cover in Canva with my touchpad, because I think it's going to make things easier for you to understand. All right, so if you go to the repo, you will see like a simple about this course, what you will learn, the kind of things that we are going to be using throughout the course. Also the specific things that you will do. A very short demo with Rick and Morty episode. Just getting started. This is something that I encourage you to do, but I will try to do it by the end of the video. Okay, when we have finally understood the three components, the MCP server, the agent API, and the UI, I'm going to show you just very quickly how to set everything up and run Kubrick on your own laptop. But if you want to skip all of this and just run Kubrick and like understand everything yourself with a self-learning approach, then you can go to this getting started markdown and start doing everything yourself. Okay, it's just a matter of creating some .envs, putting some API keys, and finally just starting everything with this make start Kubrick, which is a Docker compose command. Okay, but yeah, more things about this course. So the target audience are ML, AI engineers, software engineers, and also data engineers and scientists. Even if it's not that complex, we try to keep things technical. You will see a lot of technical stuff during this course. So yeah, I mean, you will need to know a bit about LLMs, RAG systems, embeddings, MCP a little bit. Also be proficient in Python, etc. All right, here, what's the cost? It's pretty low if you use Kubrick in a reasonable way. And finally, this is the course syllabus. This is something that both Alex and I have been posting on our newsletters on Substack. And you have here like the summary of the different articles. You can go here, check it out. And if you like the content, subscribe to both Alex and my newsletter. Okay, perfect. So yeah, and finally, these are the two sponsors, Pixeltable and Opic, which are both of them really cool tools, and we will show you how to use them for your AI projects. All right, so now that you understand the repo, just clone it. I mean, you'll have something like this, okay? I'm going to cover the structure in a little while about different folders that you will find. But previously, I just want to show you a high-level overview of the things that we are going to cover, okay? In terms of the architecture. These diagrams are going to cover the architecture of the different components that you're going to see throughout this course, okay? So, first of all, the MCP server. Let me take the vacuum. It's going to make things easier. So, the MCP server is basically the place where the prompts, the resources, and also the tools, this is the most important part, are going to be located, okay? So here you can see that we are adding a video, as the one we were adding with the Thanos clip. And this video is going to be passed through this multimodal Pixeltable pipeline, okay? This video is going to be, first of all, chunked, and it's going to be transcribed, okay? And all of these transcriptions are going to be converted into embeddings and inserted into this speech index, okay? Then we are also going to take the video, and this video is going to follow two different paths. We are going to caption the video, okay? We are going to caption the frames, and we are going to generate embeddings out of the captions of these frames, okay? We are going to store everything inside this caption index. And then we are also going to take the image, the frames, and we are going to generate embeddings out of these frames and store them inside the image index, okay? So these are the three input sources that we are going to use to generate three embedding indexes, okay? One for the speech transcriptions, another one for the captions, and the third one for the images, for the frames, okay? And here on the left, you can see, on the right, sorry, you can see the different models that we are going to use, okay? So OpenAI GPT-4o Mini Transcribe is going to be used for the transcriptions, okay? Instead of Whisper, in here, we are going to use this GPT-4o Mini Transcribe. Then we are also going to use this test embedding 3 small from OpenAI to generate the embeddings for the speech index. And the same goes in terms of the embedding model for the caption indexes. All right, for the captioning, you can see here in blue, we are using OpenAI Vision, GPT-4o Mini. And for the image indexes, for generating the embeddings, we are using this clip embedding. Okay, maybe you are already familiar with it. Okay, so this is everything related to the video engine, and this is something that Alex is going to cover later in this course. Okay, it's going to cover everything related to the multimodal video pipeline. I'm going to focus on this part, on how to build MCP servers using FastMCP, because the three indexes that we created previously with the video engine, okay, that we created in the previous step, are going to be the ones used by the MCP server, by the tools implemented inside the MCP server. All right. Here you can see, for example, this tool, and this tool is just going to run some queries, some semantic queries to the speech index, the caption index, and the image index. All right. But this is not the only kind of resource that we are going to locate inside the MCP server. We are also going to locate prompts and also some relevant resources. Okay. Important thing about prompts is that we are going to version these prompts, and we are going to do it using OPIC. This is something that I haven't found that much in many of the tutorials and many of the projects that I've been researching. Many people tend to define the projects, the prompt, inside the agent API, but we thought it would be cool to show the community how to do it inside the MCP server. That's the reason why we decided to put everything here in the MCP server, okay, all the prompts. And of course, all the prompts are going to be automatically versioned using OPIC. All right, so this is something that I'm going to cover after Alex covers all the multimodal pipeline stuff. I'm just going to show you how to do this using FastMCP, how to expose resources, how to expose prompts, and how to expose tools. All right, so let's keep scrolling down. So this is something that Alex is going to expand upon, okay? Just basically how we inspire ourselves from this paper, this video rag paper, this from archive. We talked about this in the Substack articles, so I encourage you to go to the repo and to click the different links, because you will find information about this paper inside, okay? Once we have successfully understood the MCP server and also the multimodal pipeline, I'm going to cover another important component, the second component, to be more precise, the agent API. All right, and this agent API is not going to rely on OpenAI. We are going to rely on Groq for this one. You can see here the two models that we are going to use, Llama for Scout and Llama for Maverick for the different tasks. All right, so we are going to use these models, these LLMs, to generate, to implement an agent from scratch. And that's also a good feature of this course, is that we are not going to use LangGraph, Llama Index, or any framework. We are implementing everything from scratch in terms of the agentic layer. As the API, for defining the API, of course, we are using FastAPI as always, and we are also defining some cool integrations with the MCP. And this is important because you can see here this square in yellow. MCP tools are different than Groq tools. So we need to create some layer of translation between the MCP tool and the Groq tool. And this is something that I also show you because it's really cool. And yeah, this is basically everything. Of course, we are also using OPIC for all the LLMOps related stuff. So for example, tracing the agents and logging all the different conversations and stuff like that. I will show you how to do it. And another good feature is that in this case, we can rely on specific implementations, like built-in implementations for LangGraph or for LangChain that are already implemented inside OPIC. In this case, I will show you how to do it manually, how to keep tracing all the different operations, all the different functions manually. And I also show you how to build short-term memory, a memory layer using Pixeltable, which is really cool if you want to build stateful agents. All right, so after we finish this agent API, the only thing that's missing is the user interface. And this is something that Alex is going to cover in detail in the last part of the video. He will show us how to use TypeScript and React to build chat UI, this UI that you saw previously. And yeah, that's basically something that I was missing in the previous course in Philo Agents. And many of you suggested in the comments that it would be great if we could expand a little bit the knowledge of how to build UIs using something different from Python, TypeScript in this case. So yeah, I followed your advice, and that's exactly what we are going to do in this course. All right, so I think that's everything for this short introduction about the diagram. Just remember, as a brief summary, 3 components: MCP server with the multimodal pipeline that is going to populate this MCP server. Secondly, agent API, and thirdly, the front-end UI using React and TypeScript. All right, so yeah, that's everything. And now I'm going to skip through the cursor tab and just show you a little bit about the different folders that you will find. So if you have successfully downloaded the repository, you will see something like this. Okay, let me clean the tabs. You will see 3 main folders: Kubrick API, Kubrick MCP, and Kubrick UI, that contain the 3 components that I was telling you about. By the way, the rest is basically the same as always. You have the README, make file with some useful comments that you can use to start the full project. This getting started markdown that I was telling you about at the beginning that you can follow if you want to skip everything and just start building Kubrick, start playing with it. This Docker Compose dev, Docker Compose, the final version with the 3 components I was telling you about: Kubrick MCP, Kubrick API, and finally the, Kubrick UI. And yeah, some static where we put diagram, the sponsors, some tutorials, etc. that you can check if you want. But the important stuff is located inside these 3 folders. Okay, so first of all, just going to start with the Kubrick MCP. We are going to study and to understand all the different subfolders and logic that is located inside. So this video engine, the video processor, how to define your MCP servers using FastMCP, etc. After we have finished with the Kubrick MCP, we are going to start with the Kubrick API. I'm going to show you like the different, the structure I follow for this API, all the different functionalities that we have implemented inside FastAPI, and how we have successfully implemented from scratch an agent, a Groq agent, that has also a way to translate between MCP tools and Groq tools. Okay, this is an important feature that you might use for your own projects or even translate to other LLM providers. Okay. Perfect. And finally, the Kubrick UI. This is something that Alex is going to cover in detail, as I told you before. And it's basically the React application, the React frontend that you are going to interact with when you start talking to Kubrick. So yeah, that's everything. And now, since we need to start with Kubrick MCP, I'm going to leave Alex with an amazing explanation about the multimodal pipelines using Pixeltable. So Alex, whenever you want, man.
So while we're still on this diagram, let's focus a bit on what models are we going to use for our multimodal pipeline and what's their scope within each of these processing steps. So starting with the video first, in here we get a video and adding this video to a Pixeltable. For this multimodal data pipeline, we are using Pixeltable to define a table schema. And in that schema, we have a video column that's at the root level. On top of that, we add functionality to split the video into its audio channel and its video channel. And for the audio channel, we'll be chunking it into smaller segments based on a few thresholds and parameters that we provide. And then we need to apply a speech-to-text model to get the text transcriptions from the audio, which will be putting us here at this point in the pipeline. The next step being to run all these transcription sets to an embedding model and saving the embeddings into this embedding index here. Now this will make the audio processing pipeline. Moving down to the video channel in here, we will need to sample the frames, the individual frames from the video. The next step would be to generate captions for the frames, explaining, basically feeding these images to a VLM, in this case a GPT-4o Mini, and that VLM will respond with a text description of what's happening in that image or what it had seen, or classify different objects into that image. So that will make the captions and be putting us here in the processing pipeline. And with the purple step, we'll be also embedding or generating embeddings for raw images themselves. To do that, we'll be using the clip model, which is also from OpenAI. This one is open source and is specifically designed for these types of tasks. So for that, we'll be using clip, and that will be putting us at this step in our pipeline. And we'll be ending up with generating these two embedding indexes, one for the captions, for the text descriptions of the images, and one for the images themselves at this point. So as an overview of the multimodal pipeline, that's how the process works and how everything flows through this. And now if we go into the code directly, for this video we'll be focusing on the Kubrick MCP folder, as here is where we have implemented this pipeline that we've just showcased. And more specifically, we'll be targeting this video folder, the ingestion scripts, and then the video search engine. First, let's cover this config.py script, as here we have a set of arguments and variables that are either populated from the .env file that we load, or they are hard-coded with a specific model name and some thresholds for the processing pipelines, both for the audio and for the video. So going to the config.py, here we have the settings class. This is based on the base settings object, so it inherits the base settings from Pydantic settings, which is a package that I do recommend you use if you build applications or fast API applications. I'd recommend using Pydantic settings just because it fits within the same Pydantic environment. Start with this set of variables for OPIC. Here we have the OPIC API key, the workspace and the project. Nothing fancy on this side. Followed by OpenAI, so we need to provide an OpenAI key in here because the models that we are going to use, this one, the embedding one, and the GPT-4o Mini are all from OpenAI. We're going to use them via the API. So we need the API key here. Then we have the model namings. We'll be using this mini transcribe for the generating transcripts, GPT-4o Mini for the captioning, and also this for the similarity over the transcripts to generate embeddings. We'll be using this one. And then for image embeddings, we'll be using clip. And also for caption embeddings, we'll be using also clip. So that's represented using these colors on the image diagram. So we have these embedding indexes, and each of them have their own model that does the processing. Now jumping to the following group, this refers to how we sample frames and also sample audio. So this parameter grouping here will be used at this layer where we split audio into chunks and where we sample frames from the video. And in this case, we've hard-coded a limit of 45 frames. So regardless if your video will have an 1 hour length or a 1 minute length, we'll sample 45 frames each time. Mainly that's because we are using the GPT-4o Mini to generate image captions, and we want to keep a lower cost for that. For videos that are not that long, let's say 5-minute videos or 10-minute videos, this factor works quite well. But obviously, if you want to work with a 1 hour video, by maybe longer than that, you will need to increase this factor just to gather more context from what's happening in the video. Next, we have a set of parameters for the audio. Chunking process, we have a chunk length. We set that to 10 seconds. And optionally, we also have the overlap. In this case, we allow for 1 second overlap between the audio chunks. And we specify that any audio chunk that might be a leftover, for example, at the start of the audio clip or in between audio chunks, or even at the end, if that leftover is smaller than 1 second in length, it will be skipped. This will relate to a resizing process. Second reason for the cost savings, because the way VLMs work, they use patches to split your images into smaller patches, and then those patches are encoded and sent to through the model. So in that case, a 1080p resolution will imply more patches to be generated, and then the model will consume more tokens just to understand the image and then to generate a response based on that image. So we kept this the lowest possible with a fairly good resolution that doesn't affect that image too much. So this is to save costs on also. Grouping here refers to the sampling processes from these embedding indexes, because the way now this last group of our parameters refer to how we do sampling from each embedding index. We can see here the speech index, caption index, and image index, and each time we're going to sample entries from those indexes, we'll be keeping the most confident, or the one with the highest similarity score. And in this case, for question answering, we'll be diving into how this top K factor is used and why it is containing 3 instead of 1. Okay, now this will make the entire configuration of the video or the multimodal processing pipeline and also the MCP server itself. Moving further, we'll be going into this video folder, as here we have the multimodal implementation, the ingestion folder, and here we should start at this video processor class. Now, starting at the imports, in here, since our multimodal pipeline focuses solely on Pixeltable, we'll be using the built-in Pixeltable adaptations for OpenAI API functionality. For example, if we were to check this OpenAI wrapper, we could see that we have a list of models that we can use. We have already pre-built OpenAI rate limiting. Endpoints, we should see endpoints for speech, also transcriptions, translations, and also vision endpoint, and generating text, or the generation endpoint. So that's cutting a lot of boilerplate code that we would have to add just to access various models from the OpenAI API. The same goes with clip. In this case, clip will be using it to embed images directly. And the clip wrapper comes from the Hugging Face implementation from the Pixeltable function. In this clip, we do have it based on the transformers library, where we load the clip model and clip processor. We load them from Hugging Face cache locally, and then we just run inference using these 2 lines. Moving further, the embeddings endpoint is for this model in here, and the vision endpoint is for the GPT-4o mini, which we'll be using to generate image captions. Moving next, we have another utility, extract audio. So here is also built in Pixeltable. We'll just pass in a video and we'll get the audio clip extracted automatically. So again, no boilerplate code implemented for that. And for the chunking strategies, we have these 2 iterators, also from Pixeltable. This one is for the audio clip, where we specify in the inputs the audio clip in here. Then we have the chunk duration, the overlap seconds, and the minimum chunk diversion seconds. Basically, so here, this is the parameters that we're going to pass to that audio splitter. Frame iterator works the same. It gets the video as input, and then we either pass in a FPS factor or a number of frames. In case of FPS, this is more dynamic. You could pass in to sample 1 frame per second, 2 frames per second, or the max number of frames per second a video has. Or in case of number of frames, this will be evenly distributed throughout the video. And in our example, we are selecting frames using this factor in here. This one are built-in, our Pixeltable built-in, but we also expanded and added a few custom functionality and methods. For instance, we do have this video ingestion functions. And if we dive into the functions, we have 2 basic functions in here. You might notice that this gets in a JSON file. This is the Pixeltable typing system, but underneath is just a Python dictionary. And from it, we return the text field from that dict. Moving next, we do have this resize image method where we pass in an image. This is a pillow image. So from pillow import image. For this resize image, we also pass a width and height. And if you remember in the config file, we had these two, resize width and resize height. You might have noticed that these 2 methods that we've added are decorated using this pixeltable.udf. And UDF comes from a user-defined function. And since Pixeltable is table-based, works similarly to pandas, for example, but allows for more functionality and specifically focused on multimodal processing. And UDF basically allows you to define a method and apply this method to each entry or each row from a column. We'll be seeing that in more detail as we'll be adding this custom methods that we have as computed columns into the big table schema that describes this process in here. Okay, moving next, we started with the functions. Let's go back to the video processor. We'll be skipping this for now, and let's unpack the constructor for this class. So we have the video processor. We don't take any init arguments. We instantiate the video table, the frames view, and the audio chunks. Now the video table variable here will refer to this part, since this is the root level of the table. Maybe to change the color a bit to blue. So video table code will refer to this level. Then we have the frames view and the audio chunks. Since we split the initial video into audio channel and video channel, this will be the frames view, and this is the audio chunks view. And in Pixeltable, a view is basically a render or a subtable where on top of which you could apply processing without affecting the initial table. For example, if we have this table in here as the initial one, and we have this video column, and here we have some metadata. Ignore my typing skills. And we want to create a specific view without affecting or inserting new fields into this initial table. We could just create a new view using this column. And our new view could have the same video column, but we could add many other columns without having to affect the initial table schema. And that's what we are doing with these 2 views in here. Since for the audio channel view, for example, we'll have the chunks. For each chunk, we'll have the initial transcriptions, then we have the text extracted from those transcriptions. We also have the embedding vectors in there, So a lot more columns that we need initially. Okay, moving back to the setup table method. This takes in a video name argument, and here we have a caching mechanism to check if the video that you're uploading is already processed and existing in cache. Otherwise, we just create a new table schema, define every processing step that you saw in this diagram in here, and then save the new table to the registry. The key method that sets everything up is this underscore setup table. And if we scroll down to this one, we first have the cache directory setup, then we create the table and we populate the two multimodal processing branches. Okay, diving into the setup cache, we just create the directory, the cache directory under Pixeltable's catalog, and that will give us this. So Pixeltable by default stores everything under this. In your home, you would have a Pixeltable folder, and in this Pixeltable folder we have the following structure. So I already have some files processing here. This would be longer to scroll, but if I were to just list everything, we have the file cache, the media folder, PG data. This is the database to keep the vector embeddings, and for the media we can see, or actually clear the cache beforehand, but this is the default structure that Pixeltable defines in your local cache. Okay, now moving to this create video table method. This is a simple implementation. We just populate the self.videotable object, which initially we set to none. We just assign it a new empty table. The create table structure expects you to give a table name for reference and then a schema. So this schema has to be configured as a dictionary, where the key of the dictionary is the column name and then the column type. So going into the diagram, with this first blue arrow we have the video column as the table root. So this would be the video name in here, and then we have this type of the column, which is a Pixeltable type, specifying it's a video. Additionally, a majority of methods in Pixeltable do have this if exists flag, where you could either replace, ignore, or raise an error if your table or column already exists. Now we're jumping to adding the different processing branches, one for audio, one for frame processing for the video frames. We'll be jumping into this audio processing one, and here for readability we structured it similarly as how we drawn it in this diagram. So if I were to clean all these arrows in here, we do have the audio channel first. This is a new column that we must extract and create. Then we split it into multiple audio chunks. We generate transcriptions, and then we do the embeddings for those transcriptions. Now going to the code, we have one for one. We have the add audio extraction. We create the chunks view. We add transcription. This is an additional step where we extract the actual text from the transcriptions, because with the majority of speech-to-text models, the response that you get from the model is not the actual text, but you get a dictionary with tokens, timestamps, and other metadata, and alongside that you get a text field from which you could extract the entire transcription text. Okay, and we end up by adding an embedding index, which maps to this step in here. So if we were to go under this method, we have our initial table in here, self.videotable, and we use this add computed column. The output of this method, add computed column, would be a new column with this name. This column would be called audio extract. this will be automatically added to our existing table, and the results in that column would be whatever this method in here returns. So we could see the implementation for this extract audio. Here we see the decorator UDF. Each method that you want to apply or add as a computed column has to be decorated as a user-defined function. And now this one takes a video path as input, which is exactly what we passed in here, and goes in, opens that video as a container with the context manager in here. Then it extracts the audio stream, and from this audio stream it iterates over each packet while decoding the audio signals from that packet and writing them into a new file. So here we have av.open, output file name, and inside the output container we write the new audio packets. After this finishes, we just return the new audio file name, which will be stored in the Pixeltable cache, and that's how we get the audio out from a video using Pixeltable. The next step would be to chunk our existing audio into multiple segments. And to do that, we'll jump into this create audio chunks view. So here we have self.audio chunks. This initially was set to none. Now we populate it as a Pixeltable view. We pass in the name of this new view. For reference, we need to pass the table from which we extract this new view. And then we have an iterator. So this audio splitter iterator is built in Pixeltable. This takes in the entire audio segment as input, while also taking the chunk duration, so it knows in how many chunks and how long that those chunks should be. It takes an optional argument of overlapping seconds. So for example, from chunk, if chunk 1 overlaps with chunk 2 on a span of a second, that's okay, or any other argument that you pass in here. And this one here is used to discard every chunk that's left over, let's say. So, okay, now that we've added or created this chunks view, we have our audio chunks. So we've completed this part. The next part would be to add the transcriptions functionality and use it or pass each chunk from here to a transcription model, in this case the GPT-4o mini transcribe, and extract the transcripts from there. Next step, we have this add audio transcription method, and for the implementation we follow the same structure. We have the audio chunks this time, not the initial video table, but since we work only on the audio processing branch, we use audio chunks. On this we add a computed column, and this computed column call will create a new column under this name, and the results that will be put in that column will come from this execution in here. So we have OpenAI.transcriptions, where we pass a audio segment and the model to be used. In this case, if we go to our settings, we could see that we use the GPT-4o mini transcribe to get the transcriptions. By executing this method, that will put us at this point where we need to add an embedding index over the transcriptions. To do that, we have this add audio text extraction, which is also a computed column. The name of the new column would be chunk_text, and the results in it would be the text transcriptions only. The last step is adding an embedding index, and the way to do that in Pixeltable is fairly simple. We'll just use the audio chunks view, and then similarly as for add a computed column, this time we'll be adding an embedding index. We specify the column on top of which we want to add this embedding index. Since we're working with text, we pass this string underscore embed, and then use this is from OpenAI, is the embeddings endpoint. We call it as such embeddings.using, and we just pass in the model. Now same goes for the video branch. In here we also have a frame. We create a frame view from the initial table. This will contain only the frames for the video. Then we add a frame embedding index, which in the diagram would be this step. The embedding index for the frames will give us this processing step. The frames view will represent this group in here, because we get the initial video and sample a number of frames from it. Then the next step is add frame captioning. These are the calls to OpenAI model, so this light blue branch. And in the end we have the captioning index, where we need the captions of the images and then generate embeddings for each caption. That's going to be done with this method. Now let's unpack them in a similar manner as for the audio branch. Here for the create frames view, we have the initial frames view object, which was none. We create a new view, pass in its name, pass in the table from which we'll be extracting this view, and then for the iterator, we pass a frame iterator this time. This is built in Pixeltable, and we call it with using .create, pass in the video as input and the number of frames that we want to sample from this video. This will be evenly distributed frames. Also, as part of this create frame view, we have the resize functionality for the frames. Now, in order to save on costs and make the inference over the frames to get the actual captions or image descriptions, to make it run faster and save on tokens, we'll be resizing each image to a specified resolution of 1024 by 768 pixels, and we'll be doing that automatically for each frame that we've extracted in this view. And the next step is adding the frame embedding index, and for that we do self.framesView, adding an embedding index. We specify the column on top of which we want to add it. So in this case we have the resized frame because we defined it here. Next we pass in the image embed. If you remember, here we had the string embed because we were working with text transcriptions. In this case, this being images, we pass in the image embed, and here we use clip model. So clip.using, pass in the model ID, and embedding vectors for each of the frames will be generated and stored onto this column name. The next step is to add frame captioning, and for that we use the same flow, add computed column, pass in the new column name, and then the processing function in here. With this we call the vision endpoint. You can see Pixeltable functions, OpenAI vision endpoint. This is an UDF built in from Pixeltable, which takes in a prompt, the actual image as input, and the model ID. So for the model ID we have GPT-4o mini. For the caption model prompt we have this plain prompt in here, describe what is happening in the image, and then the images rows from this column. Okay, moving next, and the last step from this pipeline is adding the embedding index on top of the generated captions. So here we have processed this, we have added this, and now we need to add an embedding index over the generated captions. So we'll do that using this call. We add an embedding index, pass in the column name, string embed, also using clip, and pass in the model ID. Okay, now that we've covered the multimodal pipeline and how it's built, let's see actually how we use functionality from it. And that happens under this ingestion folder. We have a video search engine implementation. So in here, if I would to collapse, now in the video search engine class, we do have this constructor. We pass in a video name and we search for that video name in the existing registry. So we try to get that table for an existing video that was already processed. We load that up from a registry. Just to unpack a bit how this registry works, let's go to get table. And in here we see we have a method of get registry, and this reads from local storage. We keep the latest processed table. So in this case, a table is assigned to a processed video, and from that registry we just load up the JSON. In this case, for a video name, that would be the key. We have this Pydantic base model that stores the video name, video cache path on the local storage. We also have the video table name, the frames view name, and the audio chunks view name. So all these three, video table, frames view, and audio chunks view, will help us reference each view to be able to sample from each of these embedding indexes way simpler. After we've processed this, we just return the video index registry. And in here we try to get the table by its video name. We get its metadata, and if the metadata is valid, we just return the table. So we have this cache table object, which is also a Pydantic base model. On it we have a from metadata method, which loads the metadata fields and then instantiates a new cached table. And this cache table contains the video name and the video cache as strings. And then we have the actual table objects. So in here, since we already have the video index, and from this video index object, we could access either the general table, the one with the video column at the base. We could also access the frames view and also the audio chunks view. So for these two branches in here, we have embedding indexes for both, and we will need to sample from any of those depending on the context. Now, here we have this line first, where we get the similarity scores between the query provided and the existing transcriptions texts. In the previous video processor implementation, we added an embedding index over the same column. So we have the chunk text column, and this chunk text column has an embedding index on top, such that each row from this column has its embeddings generated and stored as part of the same table. Now to compute the similarities, we have this call, video index, we get to the chunks, audio chunks view. From that we select the chunks text column, and we call this similarity with the query. Now this will yield us a result set of similarity scores for each row in this chunk text column, and from it we just sample. We need the start time second and end time second for each audio clip, and we pass in the similarities such that we order them in a descending order. Now, one important aspect on how Pixeltable works, each value from inside the column, it's actually a reference and not the actual value. For example, an image, if you have a table with 1000 images, if you load that table into memory, you won't load up the entire set of 1000 images into memory, but rather load references to them. And to actually materialize those references into actual frames, you would have to call this collect method, which will give you a data frame result set. So once you call this collect, you would get access to your raw data from that table. And to unpack this a bit, we have the results object in here. We limit the results via a top K argument that we passed in here. And then we collect the results to materialize the references into actual data. And for each entry, we get these 3 values. Now, same goes for the search by image approach, with the only difference that since we have a front-end, back-end application, from the front-end, when we upload an image and we want to search within the video using that image, we need to encode it into base64 string on the front-end side. Then when the image reaches the back-end API, we'll decode from base64 into an actual image that we can process in Python. After we decode this image from base64, we converted it to bytes and then use the image from the pillow module to load it into an actual image. Then we use the same call for the similarities. In this case, we use the video index, now with the frames view, and have the resized frame column because we added the embedding index on top of this resized frame column. So in this column, and the target image, which comes from the front end. Now we have the same result set from this frames view. We select the frame position. This column automatically generated when we used the frame iterator to go through the video and sample frames, and also return the actual image frame from this frames view. We pass in the similarities, order by the similarities. So this result set, if we have a, in this case we used a 45 frames for the from the video, and each results object we have 45 entries to it, ordered by the similarity scores. Now on the return statement, we have the same approach. We use collect to materialize the references to the actual images from this result set. We limit those responses or those results to a top K factor. And then once we get the entry, we unpack it as such. We get the start time, the end time, and the similarity score. Now the start time and the end time represent the actual frame timestamps. So this pause underscore milliseconds is the frame timestamp from within the video, and this column is automatically generated when you use the frame iterator. And we do this transformation in here because these are milliseconds. We need to transform those into seconds. And for the start time, we subtract a delta factor. And from the end time, we add a delta factor on top. So if we were to go and draw this, let's say we have a set of frames like this. Let's make 5 frames, and our target frame is here. So this is the best frame match that we've got from inside the video using the source image that we have provided. Using that delta factor, we basically expand these boundaries. And when we compose the video, we just consider all of these frames in this order. Now, the response from the agent will compose all these frames into a video and send the video back to the front end, and that's the clip that you're going to see if you asked for, if you asked the agent to get you a clip from the video, but also passed an image as input. Now moving back to the code, same goes for the caption, for the search by caption approach. We also compute the similarities in here. We get the results. And on the best image caption match, because we use the text square in here, for the best image caption match, we also do the delta frame interval. padding with n frames before the actual start time and padding with n frames after the end time. So in the end, we'll be composing the same set of frames that will be converted to a video. Here we got two more methods. We get the get speech info and get caption info. This works similar to the ones presented before, only that in this case we will search the speech index. So in order to get the similarities, we have a query. We go to the chunk text column, which are the transcripts for the actual audio chunk. We select those values, and here we return the raw text alongside the similarity score. Same goes for the caption. We go into the frames view, go to the image caption column, compute the similarity with the text query as input, get those values, sort them by similarity score, and extract the actual caption text. Now as an overview of how everything fits together. So on the first layer we had the video processor, which built the table schema and composed the overall multimodal pipeline that we had in here. On top of that we had the video search engine class, and this helps us sample from this embedding indexes that we have. And now we need to have another layer which would know which method from this video search engine class to call depending on what the agent decides to do, or what tool does the agent decide to use. And for that, since we have the video processing pipeline as part of the MCP implementation, for that we should go to the tools, the MCP tools implementations, and unpack how we use the video search engine as part of these tools. For example, in this get video clip from user query, from the front end, a video path of the newly uploaded video will be passed as input in here by the agent, and also the user query from the front end will be extracted by the agent and passed to this tool. In more detail, we have the video search engine instantiation over here, where we get the video path. And once we get the video search engine, we can just search each specific index using the user query. So now to compose the response, the video response, we initially get the original video path, and we get the start time and end time of the trimmed video clip. If we were to go into this implementation here, we will use FFmpeg. This is a CLI tool that's used to process multimedia. And to unpack this command, we have the -ss. This specifies the start time of the video, and then we have -2. This is the end time. -i means the input file, and this parameter -c, this refers to the video re-encoding process. So we are trimming the video and re-encoding the frames into another video. In this case, this is a codec. This is used to encode MP4 videos with a preset of medium. So it's a trade-off between quality and speed of compression. And then this -c with an A, this refers to the audio channel. And in this case, we don't do any re-encoding of the audio. We just copy it directly as. And before passing in the output path, we just pass this -y flag, because we'll be using this command as a subprocess, and FFmpeg tends to be interactive in that it will ask you for prompts in the CLI, so we just want to bypass that and execute this command as is without having to overwrite some files or change a few parameters directly in the CLI call. And to execute it, we have a try except block. We use subprocess package from Python, process open. We pass in the command to be run, and then capture the standard output from the terminal to the standard console, and we will be printing it as a log message. When the clip was trimmed and saved locally, we just return a video clip object with the output path and this will end up on the backend side, and the agent will know to return this path to the front end, where it will be loaded and you'll see the video sequence that you asked for.
Thanks, Alex, for that amazing explanation. So as promised, I'm going to show you the part related with FastMCP, which is the library that we are going to use to build the MCP server. You will see that it's pretty similar to FastAPI, and that's the reasoning behind the name. They wanted to build something similar to FastAPI, but for building MCP servers instead of regular APIs, right? Okay, so as you already know, as we already mentioned, we are going to expose three kinds of entities with our MCP server: prompts, resources, and tools. Okay, so I'm going to cover the three of them. Then I'm going to show you the server, how to build, how to combine everything together inside an MCP server. And finally, we will see some interesting comments that you have inside the Kubrick MCP package. Okay, so you can run locally just the MCP server, and how to inspect your MCP server using MCP Inspector, which is a tool that I really recommend if you want to interact with your MCP servers for debugging purposes, okay? Of course, in the development phase. Okay, so first of all, the prompts. As I mentioned at the beginning of the video, the prompts are not just static strings in Kubrick, they are also versioned using OPIC. And that's the reason why you will see this client opic.opic. That's the way in which we are going to define the OPIC client. Okay, so here you will see a bunch of prompts that we need to for different activities, for different features inside the agent API, inside the agent definition. First of all, we have this routing system prompt. And this is necessary because Kubrick needs to decide between the different tools that it has at its disposal. Okay, so routing system prompt. Then you have this tool use system prompt. This is the system prompt that the Groq LLMs from the agent API are going to be using when a tool is needed. Okay, and here you can see the three available tools: the get video clip from user query, the get video clip from image, and the ask question about a video I didn't show at the beginning of the demo, but you can try it out. If you remember the Thanos interaction that we have at the beginning, the get video clip from user query, this is exactly what we saw when we were asking about this. Show me the clip where there are people disintegrating. So this tool is used to get a clip from the video based on the user query. Okay. This is exactly what is going to happen. Kubrick is going to use this tool, okay, to generate the video clip. And exactly the same for the first question that we ask. Show me the clip where Thanos says you should have gone for the head. This is going to trigger the same tool, but the embedding index where the tool is going to search for information is going to be different, because in the first one, it's going to search in the speech transcription embedding index. It's going to see like a huge similarity with a specific transcription from the video where Thanos is saying you should have gone for the head. But for the second question, it's going to fetch information from the caption index, okay, from the description of the different frames. It's going to see some similarity with a frame, this one, in which there are people disintegrating. All right, so that's exactly how it works. Even if it's the same tool, the frames of the information is going to be fetched from different embedding indexes, okay? Perfect. And the get video clip from image, that's something that we have already seen, and it's pretty self-explanatory. So when we share this Rocket Raccoon image, that's going to automatically trigger this get video clip from image, all right? And this is the tool use system prompt, basically. Of course, some additional rules. So if the user has provided an image, you should always use the get video clip from image tool. And finally, some current information about, like, this is basically a Boolean that tracks if the user has provided an image in the context, okay? And finally, the general assistant prompt. This is going to be used whenever Kubrick does not need to use any kind of tool, all right? It's not the routing prompt, and it's the tool use prompt. So whenever the LLM needs to generate like a general response to the user query, it's going to use this system prompt. All right, and for each one of the prompts, you will see a function like these tiny simple methods. That what they are going to do is just to keep track of the prompt inside OPIC. So here you can see that we are trying to fetch the prompt from OPIC. If there's nothing in OPIC right now, we are going to create a new prompt. We are going to start tracking this prompt inside OPIC, and that's basically it. And we are going to use to apply the same approach for the 3 prompts that we have defined, okay? And in fact, if you go to OPIC, you will see something like this inside the prompt library. So we have the general system prompt, we have the tool use system prompt with the 3 tools that Kubrick is able to use, and finally the routing system prompt where Kubrick, what the LLM needs to decide if a tool is needed or if it's not. Okay, so this is everything for the prompts. Remember, 3 prompts are able to define all Kubrick functionalities and also keeping track of everything from inside the MCP server using OPIC. As for the resources, this is really simple. I mean, it's not even critical for Kubrick's functionality, but we just wanted to showcase that, okay, apart from tools, in MCP servers, it's possible to expose many different entities, okay? So this is what we are exposing from the tools, basically listing the tables that we have defined with Pixeltable, and also some table info that we get from the registry. This is something that Alex has shown previously. All right, as for the tools, which are arguably the most critical piece of logic inside the MCP server. So in this case, we are going to use both the video processor and the video search engine that Alex has explained really well. And we are going to use them to extract or to fetch relevant information from the embedding indexes, all right, that we have created with multimodal pipelines. So the first tool is really simple. It's just the process video tool. It's going to process a video file and prepare it for searching. So it's going to trigger all the multimodal pipelines using Pixeltable, all right? Whenever we process, whenever the agent calls this tool, it's just going to set up a table based on the video that we have just uploaded, all right? And it's going to add the video to the Pixeltable database. This is exactly what's going to happen whenever we upload a video using this button. All right, whenever we upload a video, this tool is going to be automatically called from the agent API. This MCP tool is going to be triggered. Perfect. So the next one is this get video clip from user query. It's going to accept a video path and a user query. And this is one of the tools, remember, that we defined here in the tool use system prompt, right? This get video clip from user query. And first of all, we are instantiating the video search engine, and then we are just searching in 2 different embedding indexes. Remember that this is something that I was anticipating when I was discussing the 2 different kind of questions that we were asking Kubrick at the beginning of the video. So we have here a search in the speech index, in the transcription index, these speech clips, and then another search by captions. So what is going to happen here in the speech similarities? What is going to happen is that for the first question, show me the clip where Thanos says you should have gone for the head, this speech similarity is going to be much higher than the caption similarity. For the second one, it's going to happen the opposite. The caption similarity is going to be much higher than the speech similarity. So based on this, we are just going to extract the video clip based on the most similar frame, all right? And we are going to take a few seconds previously and a few seconds after that, okay, to generate a clip for around 10-15 seconds. But you can modify that using the config. All right, and of course the output path is going to be the shared volume that we are going to use inside the Docker Compose file. In fact, if you go to Docker Compose, you will see that we have a shared volume, the shared media, and this is exactly the place where we are going to store all the generated clips, all right? And of course, if we go back to the Docker Compose, this information, these clips, are also available, let me check here, by the Kubrick UI, all right? By the UI, so this UI has access as well to all the video clips generated and stored inside this shared volume. Perfect. So this is everything for the get video clip from user query. We have something very similar for the get video clip from image. In this case, we also generate the video search engine, but we are going to make the search inside a different embedding index, the image embedding index or the frame embedding index. All right. So we are just going to make a search in one embedding index, so we don't need to compare the similarities. And we are just taking the most similar frame. All right. So when we were searching for Rocket Raccoon, that's basically what is happening. This image is going to be transformed into an embedding using OpenAI, using clip embeddings. And then we are going to search by the most similar image inside this embedding index. All right. And finally, we are just extracting the video clip again and storing the video clip, the generated video clip, inside the shared media. Perfect. And finally, we have this ask question about video. This is just a way for us to get relevant information about the video, like general questions. Like, for example, you could ask, what's the color of the gauntlet that Thanos is wearing, for example, or what's the, I don't know, the color of Thanos' skin, stuff like that, you know. I think it's not as interesting as these tools. That's the reason why in the demo I showcased the other two, but you can also try this out, okay? And this is just going to take information from the get caption info, okay, from all the descriptions that we have generated for the frames of the video that you have uploaded. And then we are just taking the answer and returning the answer as a string to the agent. All right, so all of this information about the video, about the description of the frame, is going to be included inside the context. Now that everyone is talking about context engineering, that's basically how we are engineering the context of the video. All right, all the information from the specific frame related or relevant to the user query is going to be included inside the context of the LLM to generate a response. Perfect. Well, apart from the tools, we also have these OPIC utils that contains just the configuration for OPIC connections. You can check it out. It's basically the same as the one we use for Philo agents. And finally, the most important part, this is the place where we are going to really define or expose the different entities, prompts, resources, and tools to the outside world. So this is the place where we are going to import the famous FastMCP. So in here, you will see three functions, one for each kind of entity. So first of all, we have these add MCP tools, but we are just defining the four tools that we were talking about. First of all, the process video tool. In FastMCP, you can define these descriptions, which is really cool for the agent to understand the kind of tools that it has available. The description for the process video is just process a video file and prepare it for searching. The function is the one that I've just shown you. And finally, some tags to improve the search, okay? Then we also have this get video clip from user query with also a description, descriptive information. We pass the function and add some tags, and the same goes for the get video clip from image and the ask question about video. All right, so here we are just adding to the MCP server the four tools that the agent is going to have available. And then we have these add MCP prompts. As I was saying, we also wanted to showcase how to expose prompts from MCP servers. And that's exactly what we are doing here. We are just importing the routing system prompt, the tool use system prompt, and the general system prompt. Remember that there were functions in here. We need to provide a function. And that's exactly what we are going to pass to the function attribute in here. All right, and finally, we are just defining here the MCP as FastMCP video processor. I think I missed the resources, sorry. Oh yeah, here. And here we have the MCP resources that I skipped. But yeah, it's basically these records JSON that keeps track of the different tables that we are defining inside Pixeltable. After we define the MCP, this is really similar to where, remember when we are defining some fast API application, we typically go like this. So basically the same, but for MCP, you're just changing the namings. API with MCP, that's basically it. We are running all the different functions that we have defined, that is effectually adding all the prompts, resources, and the tools to the MCP server. And finally, we are creating this function that is just a click client, okay, that you can run in here if you're running the same script. Important stuff is that we are defining streamable HTTP as the default transport, and the port is going to be 9090. Okay, this is important and relevant because now I'm going to show you how to connect your MCP server with MCP Inspector, and you need to be sure that you are defining the correct transport and that you are also defining the correct port. Otherwise, it's not going to work. All right, so this is everything I think for the MCP server. Now I'm going to show you how to run it locally. Of course, this is just one part of Kubrick. This is just the MCP server. So if you want to run Kubrick, I encourage you again to go through the getting started section. But in this case, I'm just going to show you how to start, okay, the MCP server. So in the make file inside the Kubrick MCP folder, you will see this start Kubrick MCP. All right, so you can just run this command and it will start a container, okay, a Docker container. After a few times, you will see some Ubicorn log that says that your MCP server, okay, here it is running successfully on the localhost port 9090. Now, you could be interacting with your MCP server, like manually running some scripts and sending the path to the videos and interacting with the tools or getting the prompts, etc. But Alex and I wanted to showcase a really cool way to interact, to inspect your MCP servers, and it's called MCP Inspector. We also provide a make command for this. It's called inspect Kubrick MCP, and this is going to install MCP Inspector, and it's going to open localhost for you to interact with your MCP server. All right, so now let's wait for a couple of seconds, and we should see, okay, starting MCP Inspector, and here it is. So in here, a couple of things that you need to keep track of. So first of all, the transport type has to be streamable HTTP, all right? Not Stadia.io, not SSE, okay? Streamable HTTP. That's the one that we need in this case because it's not going to be like local. And yeah, if we want for it to work, remember that we were defining in the server as the transport type the streamable HTTP. So make sure that you have this option selected. Then the URL is your local host. Remember port 9090 and MCP. So if you connect, it should appear something like this green light saying connected. In terms of authentication, I think you shouldn't need anything else, but let me know if it works in the comments and I will read you. And here you see like a bunch of cool stuff that you can do to interact with your MCP server. So first of all, we have this resources tab. You can list the different resources. Remember that we just define one, let's go to the server. We just define one kind of resources, these list tables resources. In this case, there are no tables because we haven't started Kubrick yet in this local instance of MCP server, but you can see here like the recourse JSON, etc., etc. You have also the prompts that we have defined. Remember, there are 3 prompts, and remember as well that these 3 prompts are also versioned using OPIC. And you can go here and get the prompt. And the content, you can see here that the MCP has successfully returned our this one is the routing system prompt. So you are routing assistant responsible, so it is working. And finally, the tools. We can list the different tools. Remember, we had 4 tools: the process video, get video clip from user query, get video clip from image, and ask question about video. Each one of them have a description, as you can see here, and you could even run it with your own video path here, like my local host, blah, 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 and sharing your video. I'm not going to do it because, I mean, it's better to see everything working combined, okay, like the MCP server, the agent API, and also the UI working together. but you can try this out and yeah, let me know what you think of the MCP inspector. Alex and I were really excited about trying this out. So yeah, let us know what you think. And I think this is everything for the MCP server. So what I'm going to do now is close all of these tabs to make things tidy. And I'm going to move to the next folder, which is the Kubrick API. So I'll see you in a second. All right, so let's get into the Kubrick API and let's explore how we implemented both the agent and the FastAPI layer to connect the front end and the agent API, and of course the agent API with the MCP server. So if you go into Kubrick APIs, I was saying, into Kubrick API folder, we are going to explore first of all this agent folder inside because it contains the custom implementation of our Kubrick agent, okay? Inside the agent folder, you will see this Groq folder and also a base agent Python module and a memory module. All right, so the base agent is the base implementation, the abstract base class that we are going to use for any additional agent that we are going to implement. Right now, there's a specific implementation for Groq agents, but you could do the same with Claude agents, for OpenAI agents, whatever. And the memory is just the short-term memory implementation. As I was saying at the beginning of the video, we managed to implement this short-term memory with Pixeltable. Okay, Pixeltable is going to be the way for us to attach some stateful behavior to our agent, okay, to persist all the different interaction with the user. And of course, this memory is going to be deleted whenever we stop the application, okay, the Kubrick application. But let's start first of all with this base agent, okay, because there are some cool things that I want to show you in here. So if you go to the baseagent.py, you will see this base agent class, which is the base class, as I was saying, for all the agents. And inside you will see a set of attributes that we are going to use for the agents, a name, the MCP client, where we're just using FastMCP, the FastMCP client, to define our MCP client using the MCP server. And this is basically something that we have defined in the config. If you go to the config, you will see this MCP configuration section. And in here, we are just defining the MCP server, the URL necessary, okay, for the Docker Compose application. HTTP, Kubrick MCP, 1990 MCP. All right. Perfect. So this, as I was saying, the MCP client is one of the attributes that we are going to define for our agent class. Also the memory. Remember that the memory is implemented in the memory Python module. Set of tools that we could disable if you want the agent to use only a subset of the 4 tools that we were using. You can disable tools using this attribute. And in here, we're just going to define the proper tooling and the 3 system prompts that we have implemented, okay, that we have implemented in the MCP server. As for the methods, we'll start with this setup method, this asynchronous setup method that initializes like async components for the agents. So you can see that we have to define everything inside the self MCP client session. So first of all, we are getting the tools from the MCP server. This is something that is not implemented, that you need to implement. It's an abstract method, so you need to implement it for each one of the specific classes that are going to inherit from this base class. The reason is that the tools are going to be different depending on the providers. So Groq tools are different from OpenAI tools, and for Claude tools, and for Ollama tools. So you need to be sure that these get tools is implemented for your specific classes. And of course, I will show you how to do it for Groq, and you can take that knowledge and apply it to any other LLM provider that you want to use. Okay, so that's for the tools, and then the same for the 3 system prompts that we were talking about previously. Okay, so the get routing system prompt, the get tool system use system prompt, and the get general system prompt. These prompts are also going to be fetched from the MCP server whenever the agent starts. Okay, so this is for the setup. And in here, of course, we are implementing the 3 methods that are going to be called. So the get routing system prompt, the get tool use system prompt, and the get general system prompt. And you can see that each one of these methods are going to use the MCP client to get the specific prompt from the MCP server. All right, then we also have this method for resetting the memory. We are going to use the memory class in here, and we are going to call the reset memory. Okay, that is just going to drop a Pixeltable table from the database. All right, then filter active tools. This is what is going to be called whenever we want to filter some tools. It's pretty self-explanatory, just one filter. And this discover tools is really important. It's a helper method that you can use for your custom implementations, because it's going to discover and register available tools from the MCP server. And here you can see in the docstring that this method connects to the MCP server and retrieves the list of available tools. And each tool contains metadata like name, description, and parameters. That's what we defined, if you remember, in the MCP section when we were defining all the different tools inside the FastMCP implementation. Okay, and the only thing that's going to happen here is inside the MCP client section, we are just going to list the tools and then filter by the active tools, as I was telling you, and finally just returning the tools out of the filter tools, okay? And of course, we are defining some custom errors like connection errors or general exceptions and stuff like that. All right, and finally, we have this method here, this call tool, that is just going to, using again the MCP client, it's just going to call a tool by the function name and the function arguments, and it's just going to return the MCP response. All right. And the last method, this is something that you also need to implement. Remember that this one and this one are abstract methods. You need to implement them from your custom implementations. So you need to implement a way for the agent to get the tools, and you need also a way for the agent to chat. So here you will receive a message from the user, and you will just generate all the code, implement all the code to generate an answer. But this is something that we are going to see in the Groq agent, so don't worry about it. So about the memory, before we jump into the Groq agent. So the memory, as I was saying, is implemented using Pixeltable. The memory layer is going to be persisted inside a Pixeltable table, all right? And you will see that the class is pretty self-explanatory. Well, we are defining two classes. One specifically is a pydantic model, and it's a memory record. These are the records that are going to be stored inside the Pixeltable table. And the memory record contains 4 arguments, 4 parameters, the message ID, the role, the content, and a timestamp. Timestamp is cool if you want to do some future analysis about the different interactions between Kubrick and the user. So that's the reason why we added this here. And as for the memory class, so first of all, we are creating a directory to storing all the memory related tables. We are also calling this setup table, this method right here. And in case it already exists, we are also getting the memory table, okay, from the Pixeltable database. Setting the table is really simple with Pixeltable. You just need to call the create table method from Pixeltable. And in here, you're just adding a name and defining the schema of the table that you are creating. Okay, remember that our schema, as defined by the memory record, contains the message ID, the role, the content, and the timestamp. And if it exists, it's going to ignore this command. It's not going to replace or to delete the already existing table. Some useful methods that you could use out of the memory class. So first of all, you have this reset memory. This is something that we are going to use whenever we log out the Kubrick application. And it's just going to trigger this drop directory. It's just going to delete the memory table or the memory directory and everything contained inside the memory directory. All right. Then we have the insert method. It's just going to insert a memory record. And we are just calling this insert from the memory table, from the Pixeltable table. GetAll is just going to collect all the records inside the table. GetLatest is just going to get the latest memory record, that is the latest message from the user, from the assistant. And also this get by message ID, in which we can take, we can specifically query for a specific memory record using the message ID. All right. That's basically about the memory. It's nothing that complicated. I mean, the only thing that we are doing is just to define a way to persist all the chat history inside a table. Okay, we could be using SQLite, we could be using MongoDB, we could be using Postgres, we could be using even a vector database, whatever. In this case, we are using Pixeltable to showcase that it's, even if we are already using Pixeltable for all the multimodal pipelines, it's also a good match for implementing stateful agents, all right? Okie dokie, so let's keep going, and now let's get into the specific implementation. This is the interesting part because you might want to adapt Kubrick for other LLM providers like OpenAI or Claude. So you just need to jump into this Groq folder and just check the different implementations that we have here. You will see there are two Python modules, this Groq agent.py and the Groq tool.py. Groq2.py is really important because that's the way in which we are going to translate between MCP tools and Groq tools. But we are going to cover, first of all, this Groq agent because it contains the... it just inherits from the base agent that we have just covered. So I think it's better to start this way. So this Groq agent is going to import a bunch of stuff. I'm not going to go through each one of these imports. Just going to give you a general understanding of this class. So the Groq agent, as I was saying, inherits from the base agent. So remember, you need to implement two methods by force. The first one is a way to get tools, and the other one is the chat method. The chat method is the entry point when you interact with Kubrick. So as always, we are just doing this call to attach all the different required attributes from the parent class. And here we are just defining some specific attributes for the Groq agent. So we are defining the Groq client, and here we are just defining the instructor client. This is necessary because some of the responses are going to be structured outputs. So we need a way to do it in Groq, and that's the reason why we need this instructor library. All right, you can see that the way to create this instructor client is really simple. You just need to use the instructor from Groq, add in the Groq client, and a mode. In this case, it's just instructor mode JSON. This is just a way to create structured outputs. And finally, this thread ID, right? That we will need it to log the different conversations into OPIC. Great. So first of all, implement the first required method, the first abstract method, the get tools method. And this is just going to discover the tools. Remember that this is something implemented in the base agent. And then transform tool definition. And what is this? So this is really important. This is something that I wanted to show you because, as you might be wondering, MCP tools are not directly translated into Groq tools. MCP tools have a way of structuring things, have a specific schema, have very specific parameters, etc. And you can't just take an MCP tool and plug it inside your LLM, your Groq LLM or your Groq call. All right. So that's the reason why we need a way to transform or to translate an MCP tool inside a Groq tool, inside the specific schema that you need to define Groq tools. And that's exactly what we are doing inside this Groq tool.py. All right. If you go to the bottom of the module, you will see this transform tool definition that transforms an MCP tool into a Groq tool definition dictionary. What we're doing is we are going to use this pydantic model, this Groq tool pydantic model. We are going to call this from MCP tool, this class method from MCP tool. All right. And what is happening inside this method? So from MCP tool, it's going to create the Groq tool instance from an MCP tool, and you can see in here what is happening. So first of all, we are just going to iterate through the field names and the field info of the MCP tool schema. All right, you can see here tool, input schema, properties, etc. And we are just going to define different Groq parameters. All right, the different parameters that we need to define for our tool. This Groq parameter is also a pydantic model that you can see in here. All right, it contains the type, the properties, and the required, if the parameter is required or not for your tool. Once we have all the different properties defined, you just need to define another pydantic model that is a combination of a parameter. All right, so it's the Groq parameters. It's a combination. It's a list of all of these parameters. So you're just going to create this pydantic model, Groq parameters, the properties that we have just defined in here. Remember that the properties are combined of this Groq parameter pydantic model, and required, where we are just going to access the tool input schema get required from the MCP tool. And finally, we're just creating an additional pydantic model. This is the one that we are going to return. That is this Groq function. If you go here, you can see the pydantic model for the Groq function that represents a function in a Groq tool definition and has the following fields: the name, the description, and the parameters. This pydantic model. Okay, so function, and then we are just returning the class with this pydantic model as the argument. All right, and this is exactly what we are going to return. Well, of course, not the pydantic model, but the model dump, because we want just the dictionary containing all the different information relevant or necessary for a Groq tool. But this is what is going to happen. You need to implement a specific translation between your LLM provider and your MCP tool. This is something, for example, that you don't need to do for OpenAI because it has, I think, an automatic translation. I mean, you could use FastMCP to translate directly into like the MCP tool into an OpenAI model. But for Groq, we didn't find it. And that's also the reason why we chose Groq, to show you how to do it, because you can see that, I mean, it's under 70 lines of code. So yeah, this is the way that you can do it. I encourage you to do something similar, for example, for Llama or Llama CPP, imagine, to get a grasp of how to implement these translations, all right? Because I think it's a good exercise if you want to really understand what is happening under the hood with these translations. Okay, so let's move back to the Groq agent. Now we know how to get the tools, and we know how to transform the MCP tools into Groq tools. So this get tools is going to return just a list of Groq tools. And now I'm not going to go through each one of these methods. Just going to go to the chat implementation, because this is the other one that you will need to implement. And this chat implementation is going to call all the different methods that you can see here. And later, by the way, I will give you a quick explanation of why these decorators are in place. Okay, you might suspect that it's related to OPIC and how we trace things, but yeah, I just want to show you how it looks like in the OPIC dashboard. All right, so let's go to the chat. So the chat method, remember this was also an abstract method in the base agent implementation, and it contains as arguments the message, which is a string, the video path, you can see here, and an image base64. These are not required. The only thing required is a message. Depending on the kind of interaction you're doing with Kubrick, you might need a video path, and you might need the image base64. All right. When we uploaded the Rocket Raccoon image, remember. So in that case, we were using, the image was encoded using base64, and you will receive here the base64 encoded version of the Rocket Raccoon image, for example. And yeah, that's basically it. So as I was saying, this is the main entry point for processing a user message. First of all, in here, you are just updating the current trace. This is necessary, this thread ID, if we want to log full conversations defined by a thread ID into OPIC. That's the reason why we need this OPIC context, update current trace. Then the first thing that we are going to use is this tool required. We're going to detect if a tool is necessary to solve the user query. And the first thing that we are going to check is there a video path? And secondly, should I use the tool? And this should I use the tool is just going to call the router system prompt. This is going to call the router LLM that is going to detect, that is going to decide if a tool is necessary. You can see here that we are using this Groq routing model. And in fact, if we go to the config, you can check here the different Groq models that we're going to use depending on the use case. So for the Groq routing model, we are using this Llama for Scout. For the Groq tool use model, we are using Maverick, and also for the image model and the general model. All right, perfect. So let's close this and let's go back to the routing model. And yeah, we're just using the instructor client because we need a structured output. We need a way. We need a definite answer about using a tool and not using a tool. And that's the reason why in here you will see this pydantic model, this routing response model. If you go to the models.py, you will see that in here we have a section for LLM structure outputs models. And in this specific case, we are using routing response model that contains this tool use field that has the following description: whether the user's question requires a tool or a tool call, and it's a Boolean. So it will return true or false depending of the need for a tool use. Okay, and we are returning response tool use. So we are returning a Boolean, true or false. Okay, so let's get back to the chat method. So yeah, if tool is required, we can go to the if else clause. So if tool is required, we are running a tool response, and we are going to trigger this run with tool method. This run with tool method is the most complex one of the implementation. You will see that it's quite long. Let me show you a little bit of what it does. So first of all, we are getting the tool use system prompt. Then we are building the chat history. We are generating the first response. This is not going to be done with the instructor client. We don't need a structure output in this case. We're just going to use the regular Groq client. We're using the chat history. We are using the Groq tool use model. Remember, is Llama for Maverick. We are setting the set of tools that the agent has available. The tool choice is auto, and we are just generating a response. Then we are looking for a tool calls attribute inside the response. If that's the case, we are going to go through here. If there are no tool calls, then we are just going to return a general response model. This is also another pydantic model that just contains a message with the following description. It's a string, your response to the user's question that needs to follow Kubrick's style and personality. So it's a regular response. All right, so the important stuff appears when there are tool calls, okay? And that's the reason why in here we need to iterate through the different tool calls. First of all, we are just awaiting for the tool call response. That's the reason why we need to execute tool call. And we are passing the tool call, the video path, and the image base64 if provided, of course. Then we are just logging the function response. This is the response that we are getting from the MCP server and also translated into Groq tool schemas. If the tool call function name is the get video clip from image, we are just going to update a little bit the tool response. So this is the video context. Use it to answer the user's question, and we are putting here the function response. And then we have if the function name is not the get video clip from image, we're just going to return the tool response as it is. All right. We are adding the tool response to the chat history, and then we are just detecting or selecting the specific response model that we need for the following up call to the LLM. All right. So the response model could be whether general response model or video clip response model. So if the function name that is being called is the ask question about video, we just need to return the general response model. If it's an image query or a caption query, then we need another model. All right. And if we go to the model definition, you will see that the video clip response model, apart from the message, contains an additional field that is the clip path. This is really important because this is the place where we are going to put the specific ID for the clip that is being generated, right? If we go back to Kubrick, to a Kubrick UI, each one of these clips that Kubrick fetched, that Kubrick retrieved from the API, is going to be signed with a clip path, okay? And this is exactly the clip path that we need to be stored in here in this pydantic field. Okay, so yeah, whether it is general response model or video clip response model, we need to run the follow-up response. In this case, we need the instructor client. We are passing the chat history, the Groq tool use model again, and the response model. That, remember, could be the general response model if it's an ask question about video, or the video clip response model if it's the other option. Finally, and this is just OPIC related, we are also updating, we are also pushing an attachment into OPIC. We thought it would be cool to use the recently added multimodal support in OPIC. In fact, I will show you how it looks like. So if you go to OPIC and you start interacting with Kubrick, these are the previous interactions that we did at the beginning of the video. And if you go to any of these interactions, you will see that we can add some attachments to the interaction. Okay, so here we can see that it's the interaction in which I uploaded this Rocket Raccoon image. If you keep scrolling down, you will see, for example, that this is the first frame of the query in which I was asking for show me the clip where there are people disintegrating. All right, and oops, and yeah, this is exactly how it looks like. Okay, perfect. So now that we understand how the run with tool works, there's also another option, which is the running general response. If there are no tool requires, then we are going to call this method, this response general, which we are just building the set history, and then we are just returning with the starter client a general response, all right, with no tools. This is fairly simple. Finally, the last step is to add a memory pair, to add both the user and the user query and the assistant response. We're going to add this to the memory table using the memory class that we defined previously. And finally, we are just returning this assistant message response. This is necessary because this is the response that we are going to generate, that we are going to deliver to the API that we implemented in FastAPI. This is something that we are going to see shortly. But before we move to the API, I just want to show you something. The last bit of this class. If you see each one of the methods that I've been showing you, you will see that many of them have this OPIC track, okay, these OPIC track decorators. And this is the way which we are defining all the different trace items that you can see in here. All right, for each one of the interactions that you have with Kubrick, depending on the method that is being triggered, of course, this depends on is a tool necessary, it's not, general response, video clip response, and image response, etc. Depending on each one of the specific behavior of your interaction with Kubrick, different methods are going to be triggered, and each one of these methods has a specific track option. Okay, so the chat, for example, has type general. But if you keep adding, for example, the add memory pair, that's going to be fetched from here, that's going to be called from the last line, is going to be of type general as well. But you can see here, for example, that the generate response, the response general, is of type LLM, and here the tool use is of type tool. So this is the name, the unique name that we need to add to the specific trace items, and this is really cool because it lets you define specific icons inside OPIC. So for example, this type tool means that we are adding this hammer to the tool use, okay? And the name, of course, is exactly the name that we put in here. So for example, in this implementation, in this interaction with Kubrick, we are starting with the chat as always. So you can see here this chat general. Then we are calling the router. In fact, if we go to the router response, should use tool, you can see that it is of type LLM. So we are getting into this router. You can see the name here. After that, it's necessary to use a tool. So we are going to get into the run with tool method, the name, of this trace is tool use, and it is of type tool, so that's the reason why we are using this hammer icon. Then we are getting into build chat history. So if we go to the build chat history, you will see that OPIC track build chat history, and it is of type general, so that's the reason why we are having this chain icon. And finally, the memory insertion. So if we go to the add memory pair, you can see that this trace has a unique ID of memory insertion, and the type is general as well. So that's how OPIC is going to keep track of the different traces. Okay, automatically it's going to be logging the different trace steps, the trace events into this dashboard, which is really cool. And you can of course check like the time it takes for each one, and for the nested calls inside each one of these traces. All right. So yeah, that's something that I wanted to show you. There's also something cool about the threads, because remember that we were assigning, if you go to the base agent, remember that we were assigning, this was in the Groq agent. We were assigning a UID, a thread ID, and the reason is that we also want to not just put in the traces like separately, but to also implement the threads. And threads are going to be seen like this, like a set of messages. So whenever you start the interaction with Kubrick and the agent spins up, it's going to create a thread ID and to assign the thread ID to all the subsequent messages and interactions that you have with this agent. And if you go to OPIC, you will see something like this, which is really cool. The different interactions that I've had with Kubrick in the past. Here you can see 22 messages from the thread ID, 42, that was a long conversation, 10, and the last one, in which we were just chatting at the beginning of the video, is just a total of 8 messages. Okay. Perfect. So we are just pretty close to the end of the API, because now that we understand how the Groq agent is implemented, the base agent, the memory, and also the tooling, it is time to implement, it is time to show you the API. This is the point of communication between the front end and the agentic backend, and that's the reason why it is so important. So as for the API, it's pretty straightforward. The only two things that I want to show you that are a bit different maybe from the typical vanilla FastAPI implementations is how we are using the async context manager, this lifespan function. This is typical, I mean, it's a good practice in FastAPI, but in case you don't know it, I'm just going to show you how to define like client connections, database connections, even background tasks, etc. And the other thing that is related with background tasks is how to define like long running tasks as background tasks inside FastAPI. These are the two things that I want to show you in this API, because the rest, to be honest, are really, really straightforward. Okay, so this is the API.py, as I was saying, and this is the place where we are going to define the FastAPI application. The first thing that you will see, apart from the settings, which remember that I'm a huge fan of Pydantic settings. So here you can see all the different settings that are being used by the API. But yeah, as I was saying, first of all, you will see this enum that contains the different task status. This is necessary for the background task, okay, that we are going to see later. The second function that you see, this asynchronous function, is this lifespan that is decorated with the async context manager. And this is necessary when you want to define some lifespan connections in FastAPI. Whenever the application is started, we are going to define, in this case, the Groq agent. We are going to attach this Groq agent to this app state agent. And also we are defining this dictionary that is going to keep track of the background tasks. And finally, when we stop the FastAPI application, automatically it's going to reset the memory. It's going to delete the memory table that we just created with our interaction with the agent. Perfect. How can we pass the lifespan to our FastAPI application? So really straightforward. Here you can see the FastAPI typical implementation with a title, a description, a docs URL, which is the docs, which we have the Swagger UI. And finally, the lifespan, in which we are just passing this function. Okay, so whenever the application is starting, it's just going to create our Groq agent, and it's going to create our dictionary to keep track of the background tasks. Perfect. Then we also added this CORS middleware. This is, to be honest, it's not that necessary. Just wanted to show you how you can like filter the different origins, allow different credentials, allow methods. We are allowing everything in this case. If you want to deploy this into Google Cloud, Amazon, or whatever, you can start like modifying this and allowing specific origins, allowing specific methods or specific headers and stuff like that. And finally, this is also necessary because we want to mount static files for media serving. So remember that in the Docker Compose file, we have a shared media volume. So I'm adding this media mount because this is the place where the front end is going to take the clips, images, and stuff like that. Okay, that's the reason why we needed to create this app mount. Okay, perfect. So now we start things that might seem more familiar to you. So you're defining this root call, the root endpoint, the redirects to API documentation. So it's a very typical hello world message. And here we have this method and this method are going to be related to how we handle background tasks. And why do we need background tasks? You might be asking. So whenever, let's go back to HAL 9000 to the UI. Whenever we upload a video in here, this is going to be a very long running task because we need to create all the different embedding indices. I mean, we need to transcribe, we need to generate the captions, and then we need to import, we need to store all the different embeddings inside the 3 embedding indices. So this is not going to be like 1 millisecond task. It's going to have a bit of time to complete. And that's the reason why we need background tasks inside FastAPI. This process video is just the place where we are defining these background tasks. And you can see that first of all, we are assigning a task ID to our background task. And this is the method that is going to be run by the background task. How do you add background task to your FastAPI application? It's really simple. You just need to background task, add task, and just add the asynchronous function that we have just defined. And this background task is just going to keep track or to take care of processing the video. You can see that it's just creating the MCP client and it's just running a manual tool call, a manual run of the tool that is processing the video. Of course, we didn't want to give the freedom of the agent to process your video or not. I mean, this is something that it's always going to happen, to be honest. So if you click the upload video, I mean, it's expected that the video needs to be processed. So that's the reason why this is not going to be managed by the agent. This is going to be managed manually. All right? Hope it makes sense. Why did we put it in the MCP server in that case? Because, I mean, this is not a proper tool in the sense that it's not going to be handled by the agent. We did it because we want to keep everything centralized and everything controlled inside the MCP server. It doesn't make much sense to have a tool inside the agent API and the rest of the tools inside the MCP server. That's the reason why we try to keep everything centralized in the same place. Okay, so this is exactly what is going to happen, as I was saying, with the background task. It's just going to trigger this tool. It's going to run this MCP tool and to process the video, basically. And it's going to be run as a background task. That's the reason why we need all of this. And this method is just going to track the task status. Remember that the task status has these 5 states: pending, in progress, completed, failed, or not found. And that's exactly what we are going to, the UI is going to get whenever it calls this task status endpoint. Of course, using the task ID. All right, so now we keep scrolling down. You can see this chat endpoint that has a response model of assistant message response. Remember, this is the exact response that we were generated from the chat method in the Groq agent. And this is just a regular chat with the AI assistant. We are just taking from the lifespan, remember, from the context manager, we are just taking the agent, the FastAPI request app state agent, and we are just calling the chat endpoint, the chat method, with a request, the message, the video path, and the image base64. But of course, both the video path and the image base64 might be null. Remember that they were not required. And we are just returning the response. This is the response that the UI is going to receive. We also have this reset method, the reset memory endpoint, in case the UI wants to reset the memory. This upload video, this is not the processing of the video, so don't get confused. This is the proper upload of the video. So whenever we put this here, we click this button, upload video, this is the method that is going to be called. That is going to take your video from your local system, for example, and is going to put the video inside the volume. All right? And then, of course, the background task is going to be triggered. But first of all, the UI is going to call this upload video. And finally, this get method that contains all the media. This is the way in which the UI is going to get relevant media, relevant information from the shared volume. Like, for example, when it's displaying this video from here, it's just going to get the media file, the video clip file from the shared volume using this get media. Okay, it's just passing the file path. And yeah, finally in here, we're just defining the run API method. This is a click application, a client, and we're just defining this UBCon run. Of course, this is pretty straightforward. And we are just calling the run API from inside the same module. If you want to see how the FastAPI application is containerized, you can just go to the Docker file. This is pretty straightforward as well. I mean, this is very similar to the rest of my projects. ABA, Philo agents, etc., are following the same structure using UV. And yeah, this is everything as for the API. So now I'm just going to leave Alex to give you a masterclass about the Kubrick UI and how we implemented this React frontend. So yeah, Alex, whenever you're ready, man.
Hey everyone. So in this one, we'll be going through the UI implementation. As a recap, our entire system around Kubrick has a backend API built with FastAPI in Python that hosts the agent. Then we have an MCP server that exposes tools, handles the multimodal pipelines processing, and also exposes other capabilities for the agent. And the third component in here is the UI, the front-end application that's built in React JS that communicates, it's user-facing and communicates with the backend. So here I have my browser shared. This is the UI that we've built. It has a nice inspiration from the 2001 Space Odyssey movie with the HAL 9000. Miguel came up with this idea and I quite liked it. So, React app that comes by default when you create a new React app using create React app CLI tool. Under the SRC folder, we've got the components, hooks, pages, and then the styling for the app component. This will be the entry point that puts everything together, and the main TypeScript file. This is the render object that gets the app component and attaches it to the DOM. So in React, DOM comes from Document Object Model, and it's a way of structuring web pages such that React could inject code or entire components into your browser. Now moving to the UI in here, let's go with inspect, make this smaller, and select any component in here. For example, this would be inputs. We could see that this is a div. It has an ID of this video sidebar component, which is implemented in the TypeScript file with the same name. Has a few class attributes that define its style. So the CSS styling in here, and also other components, for example, could be more nested. This one is also a div. This component's implementation is a message TypeScript file, and we also have some sub components. For example, we've got this small message of HAL 9000. Here on the top, we could see a few styling details about it, and also that it comes from the message.typescript. Now, to get the basic idea behind how React works, let's look at this beautiful web page that we have in here. And let's just draw a few more React components and go with these three. For example, all these three are part of the same web page. In the case of our UI, we could consider this right sidebar for the videos to be a component, this middle chat window to be another component, the animation on the background is another component, chat window another one, and so on. Now if we go back here, we have all these components that they could be dynamic or interactive, completely separate from each other. For example, if we have this one that contains two fields, one with a name and one with a phone number, and from within the code of this component we do execute an API call, and that API call goes to a database, and from this database we get the name and the phone number, and these values get back to the API. Then this API will communicate them back to the caller. Now this data flows in here. Usually the event, there will be a change in this component in that new data came in, so that will be usually catched by an useEffect hook, and within that hook we can update references to our fields in here. This could be two simple HTML forms, and whenever we got the data we could just populate it in here as such. And then this component will be updated from its old state, where these two fields were empty, to its new state. Now that happens while these other two components stay as they are. So that's one of the powers of how React works. It works on a component-based system. Each component is dynamic, and in each component you could implement JavaScript code or write it as TypeScript. Coming back to our UI, for example, here on the right side we have the video library. If we choose to upload a video, this one for example, we could see that this part got updated. So the video library could be considered as a separate component. Initially it was empty. Whenever we clicked on upload the video, the code inside this component updated the UI. But the other components, such as this one, the middle chat window and the chat message box, remained unchanged. Now if we go to the front-end code, one of the longer components that we have, and unpack it to see how everything works. So here we are in the index.tsx. This is a TypeScript implemented React component. In here we start with a few imports. All of these are imported from the components folder. If we go to files, we see here the src folder, components, and here we have the UI and also video sidebar message and so on. We start with those imports, and then we import the built-in useEffect hook, reference hook, and useState. The useEffect hook could be, you could think of it as logic or functionality that you add and then hook it to a specific event. For example, you could use the useEffect hook to update your page once every 3 seconds, or whenever another field in the page got updated, that useEffect hook will trigger and execute the code within its scope. Then we have useRef. This is used to bound or to bind to a specific HTML element or a component within the UI, the web page. And the useState is used to update the state or change the state of any variable or component prop that you might pass. Yeah. Okay, let's start with the interface. An interface in TypeScript is similar to how a data class or a base model with Pydantic in Python works. It just keeps an object structure. So in this case we have a message that has a string content, Boolean flag that says if it's a user message. So got the file URL, file type, and the clip path. Next we have an attached file interface. We have an uploaded video interface. Here in the uploaded video, what's important is this processing status. This could be either pending, in progress, completed, or failed. That's because we added a task pooling on the backend side. A bit more context on this. When we upload a video from the front end, it might take a while for that video to get processed. For example, you upload a 15-minute video. It might take you 5 minutes or 7 minutes to process that video, and you don't want your front end to be blocked. You want to still be able to communicate or to chat with other videos while your current video is still processing. So for that, we added a task queue on the backend, and we continuously pulling that task queue using a task ID to see if our current video has finished processing or it's still pending. So this statuses in here refer to exactly that. But with the component implementation, here we have const index. This is the component name, and then we have an arrow function, and here within the curly braces we have the component implementation. We start with a use state for the messages. In this case, messages is a list of message objects, and we have defined the message interface over here. This will be the chat history from the UI. So all the messages exchanges from you and the agent that sends the responses back, everything will be stored under this message interface as a list. Initially, so here we can see, initially we have a first message, good morning Dave, and it's exactly this messaging here. Moving next, we have a use state for the input message. This will be used to update as a string. So whenever we type a message in here, that message would be stored under this input message. We have the is typing Boolean flag. So while you'll be typing here, that Boolean flag will be true, and when you stop, it will get set to false. And then we have the attached file. This refers to the image in here. If you click and attach this image, for example, now this attached file in here will get referenced to this image that you just uploaded. Next we have uploaded videos. This is an empty list, and once you upload videos in here, that list will be populated with these videos. Then we have the active video. This will help you set between multiple videos. Let's say you uploaded 5 videos in here and you've managed to process each one of them, and then you want to select between the actual video that you want to chat with. So when you click on a video, that video will be set as the active one. And here we have a flag. We have a Boolean flag of is processing video. Now while the backend still processes your video, that flag will be true. And the upload progress, this is would be a nice animation in here, just to change between the completed state or the still uploading state. So it's just a nice tooltip that will appear in here. In this case, I don't have the MCP server, neither the agent started, so I started only the agent, the UI. So that's why we get a failed message, because this video hasn't reached the FastAPI endpoint. Okay, next we have messages and ref. This is a reference to a HTML element, which is initially null. Then we have this function in here, scroll to bottom, that uses this ref. So what happens within this, actually this line block in here with the use effect also, We have the use effect hook that whenever the messages object gets updated, for example, you type a message, the agent responds with the message, then you type another one, this block in here will scroll automatically to the latest message. Okay, moving next, we have another use effect hook. This time it is bound to the uploaded videos object, and in this case we check that whenever the uploaded videos list got updated, which means that we've loaded more videos in here, we'll check for if the active video is not set and if the length of the uploaded videos is higher than 0. That means we have at least one video in there. We just automatically set the active video as the last one in the queue. Okay, next we have another use effect. This time this is bound to uploaded videos also. But this time we are actually pulling the API to check the task status of the current uploaded video. So here we have the list of uploaded videos. For each video we check if the task ID is valid and if its processing status, which this is its initial state. If it's in progress, we look for a response from the API. So we call this endpoint of task status, passing in the task ID, and the API will check the background tasks for this specific video. It will see that either if the video finished processing or not. If it finished processing, it will return a completed status. Else, if something happened, it will return a failed status. So based on this, we'll be uploading the state of the video in here. Since I don't have the API started, this response failed, so I automatically got a failed status, which got updated in here. Okay, moving next, we have this function, generate AI response. This gets a user message as input and an optional file URL or file type. You can see that this we have a question mark in here. This represents, or in TypeScript, and also in, I guess, Objective-C, if I'm not mistaken, or Swift. This type of notation is used to mark a variable as optional. So this could be either have an actual value or be none or optional. Okay, so now from the props, in Python you would call these arguments. In TypeScript these are props, and the return type of this function is a promise. This is an asynchronous function, and we compose here we have the arrow function and the implementation. We get the request body first, like this, and we see if the file is valid. In here we check if we have an image attached. If we have one attached, we encode that as base64 string in order to be able to send the string through the network. We cannot send an image directly. A common method is to use base64 encoding for that. Now we have the video to use. We must select the video with which we want to chat, because whenever we select an image, we have to have a video selected. We insert a image here, for example, get me a clip of X, and while we send this message, we'll be using this video ID. This will be the user message, and this will be the additional image input. And that happens in here. We need to make sure we have a video selected. And for the response, we call this endpoint. So we have a chat endpoint on the API side, and in the body of this post request, we just pass the request body. And the request body in this case contains the initial message, the optional image as base64 if we upload one in here, otherwise this will be null. And the video path, so this is the video ID that we've just uploaded in here. This entire payload will get sent to the API at the chat endpoint, and then the agent would know to get the video ID, load up the pre-processed tables with all the data and embedding indexes, and then it will check the user query, see which embedding index should it access, then compose the tool call for that exact same action, query those indexes, get the responses, package them, format, and then return the responses back to the UI. So the agent response will appear in here with either a clip if you ask for a clip, or it responds in case you just asked a question about the video and you haven't asked specifically to get a short sequence from that video. We have a handle image upload, so whenever you upload an image, we just read it and set the state of the attached file. So this we use it, this is a use state, and by calling this set attached file, we just assign a value to this variable, because initially it was null. Also the same, we get handle video upload. Now we create a form data object because we need to send an actual video file to the backend side, and here we have the upload response. This is a post request where we pass in the body of this post request, we pass the form data that contains our video file. The endpoint for that is upload video, and whenever on the backend we'll capture any input on this endpoint, we'll just get the video in there and then start processing that video. If we have, or we already have the Pixeltable schema already defined with all the multimodal pipelines implemented, the only thing that we need to do is to insert this video into the video column of the table, and every processing step will happen automatically. That's one feature of how Pixeltable works. So here we get a process response back, we unpack the response, and here we update a few fields. From that response, we update these fields in here. We get the video ID, we get a new timestamp for that, the video path, the task ID assigned to the video, because in the backend the video doesn't get processed instantly. It's in a processing queue, a background tasks queue, so we get a task for that that will further pooling to see the status of that video. And moving on to the return statements, usually in React, under the return statement you have your HTML code. So everything above, it's all use state, hooks, and JavaScript code to actually add dynamic functionality to your component. And in the return statement you have is the place where you compose everything together. So you have the divs in here, where we have a few styling options for this div. We have a background animation, which is happening this nice red circles in the background. Then we have another div with the chat header. This would be the message in here. We have an horizontal line, and then we start with the chat window. Here we have the flex, overflow Y auto. This is the middle chat window. Let's hover it like this. So this is the middle chat window, and in here we iterate through our messages and create message components, where we pass in the message ID and then the message contents. So this will populate this central column in here. Next we have a chatted input component, which would be the, close this, will be this nice chat input in here. and we end up by having a sidebar on the right where we pass in the uploaded videos, current active video, and these are some hooks to be executed whenever something from this component changes. For example, if we delete, if we play a video, if we delete a video, these three hooks in here will take care of that. And the final line is in this is to export this component. If we go to the app script in here, we see we import the index, which composes our entire UI flow. We create a new app component. We define a browser router. We didn't necessarily need to do this as we don't have any more routes, but just to showcase in case we would have here 10 or 15 routes or going through query parameters such as this one, and then maybe having two. So in case you have multiple routes, this actually makes sense because each sub query path will route to a specific component, but in this case we have a simple UI implementation, so we just use the home one to point directly to the index. So whenever you open the UI, you'll get directly this central view. Then we export the app, and in the main TypeScript, this is the main entry point. We just get reference to the DOM and render the application. So yeah, I hope this made things more clearer on how the UI side works, and I hope that I gave you a few insights on how React works and how we've built this UI, what components do we have, and most importantly, what calls do we do to the API agent.
Thanks, Alex, for making React understandable for AI people. So yeah, friends, we are really close to the end. I think we've managed to put forward almost 3 hours of recorded content, so I really hope that this is useful for you. But before we leave, before both Alex and I leave, I just wanted to show you one last bit of information. So if you go to the parent folder, to the parent directory, and you go to the Getting Started Markdown, you will see something like this, okay? And it's a detailed set of instructions to start Kubrick, not just as individual pieces, because Alex and I have been covering the Kubrick API, the Kubrick MCP, and the Kubrick UI, but individually. No, in this case, getting started is just a way to combine everything and to show you how to start this Docker Compose application. The first thing you'll need to do, apart from cloning the repository and installing UV, is setting up the MCP server. And to do that, you just need to go to the MCP, the Kubrick MCP, and follow this README file. All right, that's basically it. The things that you might need to do are basically creating a .env file. That's the important stuff. Because if you go to the .env example, you will see that we need OpenAI API key and some OPIC relevant keys. All right, so that's the reason why you need to create this .env and put your own specific keys inside. Otherwise, Kubrick is not going to work. Apart from that, you need to do exactly the same with the Kubrick API. So if you go to the Kubrick API, you just need to do the same, go to the specific README, and then create this .env with the new API keys. In this case, instead of the OpenAI API key, I'm using this Groq API key, because remember that for the API, we are using Groq. All right, and finally, just start the application using this command, this make start Kubrick. And if you go to the terminal and you run this, you should see in a couple of minutes, because it's going to take a bit of time, you will see the Kubrick application, the Docker Compose application in your Docker desktop, in your terminal, if you're checking the different containers in your terminal. All right, so that's basically everything for today. It's been really exciting to show you this project with you, this combination of video agents, multimodal pipelines, and MCP servers. Hope you have had a great time working with us throughout these tutorials. And yeah, I'll see you in the next video. Ciao, builders.